So I think in my abstract, I said something very vague, like I, talk about uniqueness and non-uniqueness in percolation. The first talk will be sort of introductory stuff, and then the second talk will be, new research. So I hadn't really decided what I was going to do in that second talk when I wrote that abstract. You could probably tell. So I decided in the end, what I'm going to do tomorrow is I'm going to talk about this new or newer work on understanding the analogs of all this classical infinite graph theory, but on finite transitive graphs. Okay, so the first talk is all going to be in the infinite world, and I'm going to be reviewing stuff that was mostly done 20 plus years ago. But while I'm going through that, even if you've seen it before, what I want to encourage you to think about is what, if anything, is this proof going to tell us about finite graphs, and understanding why they're actually kind of technical challenges to go from the infinite theory to the finite theory. You might think it's the other way around, but usually the finite theory is actually more difficult. Okay, so let's just start off with the basics. So I'm going to always have a graph G, and I'll always take all my graphs will be connected, locally finite. So this means that every vertex has finite degree, i.e. finitely many edges coming out of it. And I'm basically always going to assume that it's transitive. Okay, so transitive for me means vertex transitive. So that means that for any two vertices, there exists an automorphism with sending U to V. So less formally, what that means is every vertex looks the same, right? For any two vertices, there's a symmetry of the graph that maps one to the other. Every vertex plays the same role. Okay, so then I'm going to be interested in Bernoulli bond percolation. So what that means is that we're just going to take omega to be a random subgraph, where for me a subgraph is going to be a set of edges, where each edge is included independently with probability p. Okay, so p is just a parameter. So in other words, for each edge, I'm flipping a coin. It has probability p of being heads, 1 minus p of being tails. I'm going to keep every edge where I see a head and delete every edge where I see a tail. Okay, and generally speaking, what people are interested in percolation is, what does this random subgraph look like, right? In particular, what do the connected components of this random graph look like? Okay, so some of the standard stuff to know is that the edges with, so I'll also sometimes write like E belongs to omega. I kind of think of it as a set of edges or as an indicator function, as I like. These edges that we keep are called open, and the edges that we delete are called closed. Okay, this is just a standard piece of terminology in this area. And the connected components are called clusters. Good. Okay, so the first thing that sort of the first theorem about this model that kind of makes it interesting in some sense is that it typically undergoes a phase transition. Okay, so given a graph G, we define PC of G to be the infemal value of P such that infinite clusters exist with positive probability. Okay, now in fact, this event that infinite clusters exist is a tail event for all these independent coin flips. So equivalently, in fact, once it has positive probability, it must have probability 1. Okay, and typically we have that PC is strictly between 0 and 1. Okay, so you really do have a phase transition. You really do have these two phases where first you have no infinite clusters and then you have infinite clusters. Okay, and both of these things are holding almost surely. Okay, now one thing to notice here, which is which is something I won't really go into in this talk, but it's a subject to a lot of the deep and interesting questions, is that of course this definition tells you nothing about what happens at this boundary point itself, and that's a very hard question to understand. Okay, so so let's start with a basic, let's start with something even more basic. So it turns out that this inequality, the fact that PC is not 0, is very easy, okay? In fact, what we always have is that PC is at least 1 over the degree minus 1, okay? Where the degree, again, means the number of edges incident to any vertex, they're all the same, okay? Now, why is this true? So this is something that you can prove just using an elementary counting argument, right? You can say, well, suppose I look at the expected number of open paths of length n. So it's simple. So, you know, paths that don't visit any vertex more than once. How many are there of length n? Well, each such path is open with probability p to the n, right? Just the number of edges that are in the path, right? Well, so this is actually an equality, p to the n times the number of starting at the origin. So the origin, I'm just fix your favorite vertex of the graph. It doesn't matter which one you fix because they all have the same role. Okay, so it's p to the n times the number of paths from right? But now we can get an easy bound on this number of paths. It's at most the degree times the degree minus 1 to the n minus 1, right? This is just because at the first step, you can jump to any neighbor, and then at each subsequent step, you don't want to immediately go back to where you came from, so you have at most degree minus 1 choice, right? So, so this gives you a bound, right? It's p to the n degree minus 1 to the n minus 1, right? And what we get is that if p is less than 1 over degree minus 1, then the expected, this expectation here goes to 0. Right? So that means by Markov's inequality, the probability that you have any open paths, simple open paths of length n goes to 0 with n, right? And this means you can't have an infinite cluster, right? Because if you had an infinite cluster, you would have a simple open path of every length, right? So just by continuity of measure, this means that p is less than or equal. So this fact that you have a phase where there are no infinite clusters, this follows very easily by elementary counting argument. Okay, and this just works for any graph. Now, the question of whether you have PC strictly less than 1 turns out to be much more subtle. But let's consider the case of the square grid. Okay, and this is probably, I mean, maybe other than a tree, the first example that was shown to have a phase transition. So this is shown using what's called the Piles argument. So this is an argument that was come up with by Rudolf Piles, I think in like the 1950s or 40s. So he was studying the Ising model, but the same proof, it's actually a simpler proof even for percolation. And the idea is as follows. So you imagine you have your square grid. Okay. Now, and let's say this is the origin. Yep. Simple just means don't use the same vertex twice. You know, of course, I'm bounding those by non-backtracking ones, but yeah. Okay. So here's the idea. Suppose you are doing percolation on the square grid, and that the origin is in a finite cluster. Okay, so whatever it is, it's something that contains a bunch of edges, something like that. Okay. Now, so how it works. If you look at such a cluster, and you consider the dual edges that's not an example, that trace around its boundary, right, looks something like this. Okay, so any finite cluster is surrounded by this path of this dual circuit where all these dual edges are orthogonal to a primal edge which is closed, right? So, and then what we can do is we can try to count, do a similar counting argument, but using this dual circuit picture. Okay, so let's say in order for if the origin in finite cluster, then there exists a closed dual circuit surrounding. Okay, now in particular, then this dual circuit must cross the real line at some point, right? So if this has size n, then it must cross the real axis in this interval from 0 to n. Okay, so how many are there? Well, each one that has length n, the probability that all of those edges are closed is 1 minus p to the n. And how many of them are there? Well, we can do something similar again. So we have to start, it has to cross this interval somewhere. We get n choices of where it can cross. And then it has to somehow go around, and you can see it has at most 3 choices every time. Okay, so you can do something very similar. So this means that by Markov, the probability that the origin is not connected to infinity, in other words, that it's in a finite cluster, is at most this sum, 1 minus ppn and 3pn. And you can see if you take p close enough to 1, then this is less than 1 for p sufficiently large. Okay, because it's almost a geometric series. I mean, it has this n in it as well. But cool. So, so this proves that PC of the square grid is strictly less than 1. And you can imagine if you actually do the computations, you can get a simple explicit upper bound on here that's reasonably good. Okay. Now, in fact, once you know that you have a phase transition for the square grid, you can deduce that you have phase transitions for lots of other examples because they're going to contain the square grid as a subgraph. Okay, and so, for example, if you look at ZD, the d-dimensional grid with d at least 3, well, it contains z squared as a subgraph, which implies that it also has PC less than 1. Okay. In fact, this bound is not very good. I mean, PC, you'll deduce that PC of this is smaller than PC of z squared. In fact, we know that it strictly decreases every dimension. Okay. But in particular, we know that you have phase transitions in most examples. Okay. And in fact, this is now understood very well indeed. So this is quite a recent result, though. So this is Dumno-Copin. Hopefully I remember all the authors. Goswami, Ralphie, Severo, and Yudin. I apologize to any if there was another author I left off. But PC of G is equal to 1 if and only if G is one-dimensional. Okay, so I should have mentioned right away that, of course, one case where you don't have this is the integers, right? If you or like a cylinder or something like that, right? If you have the integers, it's kind of obvious that as soon as p is strictly less than 1, you're never going to get infinite clusters, because as soon as you have a positive probability of deleting anything, you're going to cut z up into finite intervals. Okay, but basically this theorem says that more or less this is the only way of having, within the class of transitive graphs, this is the only way of having not having a phase transition. Okay, and I should mention that when they proved this, this is from like 2017 or something. When they proved this, this was actually already known in like most cases. So it was known if your graph has polynomial volume growth or if it has exponential volume growth. So this was only actually open for groups of intermediate growth, which many of you will know about, I guess, in this audience, but they're kind of weird. So it's very nice to have a completely general theorem, but in fact, it was already known in most non-pathological examples. I think it was also known for the Grigorchuk group, which is like the one group of intermediate growth that most people know. Okay, cool. So that's what I wanted to say about this PC lesson one thing. Maybe one thing I should mention as well is that, okay, for this specific example of the square grid, we kind of did some estimates and we got that PC is like, I don't know, between a third and whatever you get out of this argument. I can't remember, let's say 4/5 or something. But in fact, it's a theorem of Keston from the 80s that in this specific example, PC of the square grid is a half. Okay. Now, this is to do with the fact that the square grid is its own planar dual. That's really why you get a half. And this is an important theorem especially if you want to study percolation on the square grid. On the other hand, I should say that it's liable to give you the wrong impression if you're new to the subject, because being able to compute PC is highly atypical. Okay. Usually in most examples, you're not going to know what PC is, and you have to use methods that are, more implicit, just using the definition of PC as the point where infinite clusters appear without being able to compute it. Okay. Okay, cool. So one thing I should mention, so as I said, tomorrow I'm going to tell you about percolation on finite graphs. And I should say all these things, including things that seem quite simple, become much more delicate in the finite graph world. Okay, so in the finite graph world, what you want to do is instead of studying infinite clusters, you want to study giant clusters, right? So these are clusters that contain a positive proportion of all the vertices. And some of these basic things just don't work anymore. Like, for example, this argument here, where we said, well, ZD, well, it contains Z squared as a subgraph. So if Z squared has infinite clusters, you'll get an infinite cluster here. But, for giant clusters, this argument really doesn't work. I mean, well, you have this subgraph and you'll have a cluster that has, if you have a giant cluster there, you'll have a cluster with whose intersection with that subgraph has positive density, but that's not at all what you want to know. So, even this very basic thing that, we gave like no thought to at all, that actually breaks very badly in the finite world. Okay, cool. Good. So what do I want to say next? Okay, so once we know that we have phase transitions, perhaps the next most natural question is to study how many infinite clusters do you have in the supercritical phase, right? Or generally, we'd like to understand what do these infinite supercritical clusters look like. Probably the most basic question is there just one of them, or are there infinitely many? Okay, so let's say n, let's fix some fixed g, which is infinite, and everything else, right? Connected, locally finite, transitive. And let's take n to be the number of infinite components. Okay, so one basic thing is that for each p, there exists k, which is a natural number, including 0 for the purposes of this talk, or infinity, and such that we have exactly that many infinite clusters almost surely, right? Where this p sub p means the law of the Bernoulli bond percolation with parameter p. Okay, now why is this true? Well, this is just because omega is ergodic. Right? This means if you have any event, or any automorphism event, automorphism invariant event. Okay, so if you have any event where applying an automorphism to the configuration does not change whether or not the event holds, then this event must have probability 0, 1, right? This is just what it means for a measure to be ergodic. Probably for this audience, I don't really need to tell you why Bernoulli measures are ergodic, but well, to give you the 10-second version, if you start with an invariant event, because events are measurable, what it means to be an event, you can approximate that event by a cylinder event, i.e. something that only depends on the state of finitely many edges, right? But you also know, because the event's invariant, it must also be approximated by any like translated that cylinder event, right? So then you can like translate the cylinder event off of itself, and you get that the event that you started with is approximately independent of itself, right? And therefore, taking the limit as the approximation gets better and better, you get that it must have probability 0, 1 just because it's equal to its own square. Okay. Now, another thing to mention, in advance of my talk tomorrow, is these kind of ergodicity considerations. They really, really don't work when you go to the finite graph world, right? This whole proof I just sketched of, ergodicity, for example, I mean, it's just not true that they're ergodic in the finite graph world, right? Like you can just ask, okay, is the number of open edges more than p times the number of edges, right? This is an invariant event, but actually this event has probability about a half by the central limit theorem. So you really can't use ergodicity in the finite graph world. So this is one thing to bear in mind here. I mean, it's really, when you use this, it tends to tell you nothing about the finite graph world. Okay, so, but of course, once you know that it's ergodic, this lemma follows for free just because having k infinite clusters is an invariant event. So each such k must give you 0, 1. They have to sum to 1, so there must be one that's 1 and the rest of it is 0. Okay, so the next thing this is the theorem of Newman and Schulman from the early 80s, I think, that in fact, this number of infinite clusters always belongs to 0, 1, or infinity, okay? And to stress, everything I'm talking about here is for the transitive case. Of course, this is not true without transitivity, okay? And their argument is basically that, well, suppose it's not. Suppose there's some other number, okay, a finite number that's not 1 or 0. Then if I take some growing sequence of finite sets, like the balls in the graph, for example, then eventually the ball must intersect every cluster, right? So I can find a large ball where the probability that it intersects every cluster is at least a half, say. I really just need it to be positive. Okay. But then that means that the probability that if I if I just insert all the edges of the ball into my configuration, this must also be positive, right? In fact, it's just larger than this probability. Right? If the ball intersects every cluster and I turn all the edges in the ball on, I now have a unique infinite cluster. Okay. But now, if I just observe what's outside the ball and not the edges that are inside the ball, I have a positive probability. In fact, just that doesn't even depend on what I saw outside, that all the edges are on. So I get that, in fact, I have a positive probability of having a single infinite cluster, but this is a contradiction because I assumed that I had this other number on my shoulder. Okay, and this is basically the, okay, of course, there are some details that you could go through, which I don't have time for today, but that's basically how it goes. Okay, good. So again, you can think a bit about what this is going to tell you in the finite case, and the answer is not very much. It tells you, like, if you have a bunch of big clusters intersecting a set with positive probability, then you have one big cluster intersecting that set with positive probability. But actually, when you go from this positive number to this positive number, you lose something like exponential in the size of the box. So quantitatively, this is a very poor argument. Okay. Good. Okay. So this tells us we always have just 0, 1, or infinity clusters. Okay. And the next theorem, which I'm not really going to tell you the proof of, but I'll explain some of the idea. So this is due to Hagström, Harris, and Schumann from the late 90s. And what they show is that basically the following picture holds in general. So if you define Pu to be the infemal value of P, where you get a unique infinite cluster, okay? So clearly PC is less than or equal to Pu. And what they show is that you really see this picture. So there are most of these three phases in this order. So first you'll have up to PC, you'll have no infinite clusters. Then possibly you'll have a phase between PC and Pu. Of course, these could be equal, in which case this phase is empty, where you have infinitely many infinite clusters. And then finally, you have a phase with a single infinite cluster. Okay, so basically the content of the theorem is that once you're above Pu, you always have a unique infinite cluster. Okay, and this is really not obvious because having a unique infinite cluster, it's not pointwise a monotone function of the configuration, right? Generally, if you have just a monotone function of the configuration, then it will always be monotone with respect to the probability, but this function is not monotone, right? I mean, I could have a unique infinite cluster, and then I add some more edges that just create another infinite cluster somewhere else, right? But what they showed is that this doesn't happen. Once you have a unique infinite cluster, you can't like separately spawn another infinite cluster somewhere else in the graph. It always gets instantly merged. Yeah. No, it's not, right? Because this is the infimum, but you don't know. It could be that you see like right? Yeah. Yeah. But this doesn't happen. In fact, really what they prove in their paper is a really strong version of this theorem, which says that, so there's a natural way of coupling together all the different p-values of percolation simultaneously, where you put a uniform 0, 1 label on each edge, and then you look at, you say omega p is all the edges that have label at most p. This gives you a way of simultaneously putting all the different parameter percolation on the same probability space. And they show that actually, within that coupling, there is almost surely no value of P above PU that gives you more than one infinite cluster. So that the distinction between these might be a bit subtle if you haven't thought about these issues before, but it's actually a much stronger thing. Like it could be a priori, even once you know this, that in this coupling, there are some like random exceptional values of P that give you weird behavior, but that doesn't happen. Okay, so, and I'll come back. I'm not going to explain anything about this for now, but I'll say a bit about the proof later on. So, of course, what this theorem doesn't say is that these three phases are actually non-empty. I mean, we've seen that this first one is always non-empty. PC is always bigger than 0. But if you take, for example, ZD, then we actually have PC equals PU. So this middle phase is degenerate. And if you have like the free group, or, you know, as I prefer to think of it, you know, a regular tree, then PU is 1, but PC is less than 1. So in this case where you have like a tree, you get that this final phase is degenerate. But there are also examples where you get all three phases being non-degenerate. So for example, tessellations of hyperbolic. Get all three phases. Okay. So, okay. So one of the big conjectures in this area, which is still very much open, is exactly this question of when do you have this middle phase? Is that PC is less than PU if and only if G is non-amenable. So I'll define that in a second. Okay. So what does non-amenable mean? So for any graph, we can define its Cheeger constant to be the infimum of so I look over all finite sets of vertices, and I look at the ratio of the size of their boundary to the size of their volume, okay? Usually the best way to define it is doing everything with edges, so it's the edge boundary and the edge volume. I'm only going to be interested in whether it's positive or not in this talk, so it doesn't make a difference. And you say that G is amenable if the Cheeger constant is 0, and non-amenable if it's positive. Okay, so non-amenable graphs are the ones where there's a uniform lower bound on the ratio of the boundary to the volume of any finite set of vertices. Okay, so the classical example, well, is that, for example, ZD is amenable because if you take a big box, its boundary is much smaller than its volume. And these two examples are both non-amenable trees, regular trees of degree at least 3, and tessellations of hyperbolic space. Okay, and so in fact, the amenable case of this conjecture has been understood since before the conjecture was made. So in the 80s, this problem was first solved by Eisenman, Kasten, Newman, and then there was a much simpler proof, a more general proof given by Burton and Keene. It's like 2 years later, which is the one people usually learn now, which is, well, they really proved that on ZD, you always have at most one infinite cluster for all P. Okay, but in fact, the proof works for any amenable transitive graph, so you know exactly the same proof. On the other hand, you know, the non-amenable case of this, saying that if you're non-amenable, then you have this non-trivial interval of points where you have infinitely many infinite clusters. This is still very much open. There's a bunch of cases that have been understood. How much longer am I talking for? It's 10:52 now. Okay. Okay, cool. I'll just say, well, one thing we do know is that for every non-amenable group, there's at least one Cayley graph where the conjecture is true. In fact, the way that proofs works, they show that, you know, if rather than just knowing that this Cheeger constant is positive, you know that it's like almost as large as it can be, then you can prove that it works. Actually, they use spectral radius instead of Cheeger constant, but whatever. And then they show that any non-amenable Cayley graph has like at least one generating set where that stronger assumption holds. Okay. Other than that, so I showed that it's true for any hyperbolic group, so or any transitive graph which is Gromov hyperbolic. So you know this example, any tessellation hyperbolic space in any dimension, we know that this is true for. The planar case had been done a long time before that by Benjamin and Schramm and Steve Valley. Yeah, there's a few other cases that are known, but the general case is very open. I mean, in particular, I don't think there are any arguments that start like just really using the non-amenability of the graph. Like it's always like you have some other assumption that maybe implies non-amenability, but you don't really use the non-amenability. You only use that, like, you know, like in the hyperbolic case, you have tons of geometry that you can use. The non-amenability per se does not really come into the argument. So I think there's really like a big idea that is missing for this conjecture. Maybe I can mention one other conjecture, which is due to the same authors, which is that PU is strictly less than 1 if and only if G is one-ended. Okay, so I won't go, if you don't know what one-ended is, it basically means if you cut out any finite region of G, there's at most one infinite connected component in the complement. Okay, and this is known for Cayley graphs of finitely presented groups, where it's a theorem of Babson and Benjamini. But the general case is open, and to be honest, this conjecture has been worked on a lot less than this one, and I wouldn't be surprised if it was false. You know, I think you know, if you're someone, I don't know if there are people like this in this audience who like to construct weird groups. You know, I think this is a really nice problem. You know, try to build a weird group that's like one-ended, but like barely, you know, something like that. You can maybe build a counterexample of this. I wouldn't be so surprised. Okay, so maybe just let me, in the remaining minutes, let me give you a very quick proof of this, of the Birkin-Keene theorem. Okay, so it's not really going to be a proof, but just, you know, an indication of a proof. So here's the idea. So this is the Birkin-Keene proof. So they say, first of all, they say, suppose you have multiple, actually, they just want to say you have more than 3 infinite clusters. In fact, we already know then you must have infinitely many, but the argument just needs 3. Okay. Then they say that, you know, similarly to what we did before, where we took a ball and then we kind of messed around with what's inside, by messing around, like forcing some edges to be open, some edges to be closed, you can, with at the cost of some finite probability, force this event to happen, where you create what's called a trifurcation. So this is a vertex that belongs to an infinite cluster, and if you were to delete that vertex from its cluster, it would split the infinite cluster up into at least 3 infinite pieces. Okay. Now, if trifurcations exist with positive probability, well, the model is translation invariant, so every vertex must have the same probability of being a trifurcation. So every vertex has some constant probability of being a trifurcation. Okay, and then what they say is, well, take a big box, okay? Except we're going to prove the general amenable case, so pick a big set whose boundary is much smaller than its volume. Right, lambda. Okay. Now, the expected number of trifurcations in lambda so I'll write V in T, where T is the set of trifurcations. Well, this is just equal to C times the size of lambda by linearity of expectation. Right, so you get all these trifurcations. They all kind of go off to infinity. Something like this. Okay. Now there's a combinatorial fact which says that let me make sure I state this correctly, is that there exists a set of disjoint infinite open paths from lambda to infinity of size at least the number of trifurcation points in lambda. Okay, this is something, it's kind of like an Euler's formula type thing ultimately, but you can see that this is true in this example, I hope. And this just generally that this is just a combinatorial thing. It holds for any configuration, right? It's nothing about Bernoulli percolation specifically. Okay. But on the other hand, this set of disjoint paths, it's trivially at most the number of edges in the boundary of the set, right? Because each such path must begin on some edge, which must be in the edge boundary, right? So what you get is that the edge boundary of lambda is at least C times the size of lambda, right? But this holds for any set. So this implies that the Cheeger constant is at least C. Okay. So if you like, you can phrase this as a proof by contradiction. You can also phrase it as a proof not by contradiction, that if you have infinitely many infinite clusters, then you must be non-amenable, right? Because we've actually produced a positive lower bound on the Cheeger constant. Okay. So again, in preparation for tomorrow, it's worth thinking about what this would tell you, what this argument would tell you if you tried to run it in the finite graph case. And it does have some content. It's just not really what you want to learn, right? So what it really tells you is that if you fix a small region and you ask what's the probability that I have like 3 big arms coming out of it, like for example, if we work on ZD and we just say, can I bound the probability that this is not like a global trifurcation, but it's just a trifurcation like up to scale R, that I have these 3 disjoint ways of reaching the boundary, the size R, and it does actually give you a bound on this. It's like the probability of this event is at most 1 over R or something like that. I mean, constant over R. Okay, so it does have some quantitative content. It's not going to tell us about the uniqueness of the giant cluster or anything like that. It's going to tell us that if you have more than one giant, they can't like always be, their boundaries can't kind of be space filling or something. It's a much weaker conclusion than you would like to learn. Okay. So I guess that's a good time for me to stop. So thanks for your attention. Yep. Yeah, so that's a really interesting question. So this thing that it's always 0, 1, or infinity, that's obviously still true. The question is, PC could belong to, you don't learn about which phase the boundary point belongs to, right? So this is a very subtle question. So the conjecture, first of all, is that you always have no infinite clusters at PC, provided PC is less than 1. So in other words, if you're not one-dimensional, then you should have no infinite clusters at PC. But this is a major open problem. In fact, so the status of this is that actually in the kind of world of big groups, we understand this pretty well. So Benjamini, Lyons, Perez, and Schramm proved that for non-amenable groups, this is true. As in my PhD thesis, I showed it that it's true for exponential growth groups that might be amenable. On the other hand, and we even got some results about intermediate growth. If anyone's interested in that, I can tell you about. And then on the other hand, in the classical case of Euclidean lattices, so it's known that in the 2D grid, you have no infinite clusters at PC. That's the theorem of Kasten. And it's known that in high dimensional grids, you have no infinite clusters at PC. This is due to basically to Hara and Slade in the 90s, where high, well, when they did it, it was like D at least 19. Morally, their proof should work down to strictly larger than 6, but it requires like computer assistance. So, but in particular, dimensions 3, 4, and 5, and to some extent 6 are like very, very open and are probably the hardest cases. And then of course you have like, you know, nilpotent groups and stuff like that maybe answer different from the Euclidean case. There's also the question of what happens at PU. This is very subtle, and currently there are not very many examples where it's understood. So we know that, so of course this question is only interesting in the non-amenable case, otherwise it's the same as the PC question. We know that there are some examples where you get uniqueness here, some examples where you get non-uniqueness, and we don't really know how to tell in a given example whether you should have one or the other. We also don't know that, like, it could even be that if you have a group, there might be different Cayley graphs, so one has one property and one has the other. We don't know that that isn't the case. Yeah. Yeah. Just as a subgroup. Yeah, no, I wouldn't say so. No. Yeah, these things are always like, the behavior of percolation is very delicate. It tends to be, for questions about P very close to 0 or close to 1, you can use all this kind of quasi-isometries and stuff like that. But really asking about criticality, it gets less, these kind of notions become much less useful. Although the cost is useful for some of these questions. Yeah. Yeah, so it's still defined. It's just that, and the proof that it's positive works in complete generality. I mean, for bounded degree graphs. And of course, you know, just proving that it's less than 1. There are some nice conjectures, actually. So there's a conjecture also from the same paper of Benjamin and Schramm. They have this famous paper called like Percolation Beyond ZD, Many Questions and a Few Answers, that has a lot of these conjectures. And one of their conjectures is that if you have any graph and it satisfies an isoparametric inequality of dimension larger than 1, so in other words, like every set satisfies an inequality like this, then that should be sufficient to have PC less than 1. But this is open. There's a paper by Augusto Tejera that proves something quite similar to this, but he needs slightly stronger, less natural hypotheses. Hi, how's it going?